G'day, in this video we're going to be focusing on a variety of concepts including nuclear transmutations as well as concepts surrounding energy and mass defect. This video covers a variety of dot points at the end of inquiry question 4, all to do with various processes called nuclear transmutations, some of which we've already looked at already, some of which are going to be a little bit new today. Some of these new processes include nuclear fission and nuclear fusion. The common thread that we're going to have to explore all of these concepts are these things down here: the law of conservation of energy, the concept of mass defect and binding energy, and relating it all through Einstein's mass energy equivalence. Beginning of this lesson, we're going to be talking a little bit about units of measurement and the idea that we can account for mass and energy using various quantities, particularly focusing on atomic mass units and doing a bit of a recap on electron volts for energy. We're also going to be looking at how we get the strong nuclear force and how it's connected to this concept of mass defect in nuclear processes. From there, we'll start unpacking different types of nuclear transmutation and look at some examples. Again, we've seen some already and others might be a little bit new today. And then we'll unpack fission and fusion. And throughout this process, when we look at these different types of transmutations, we're going to be looking at this idea of mass defect and those concepts to explain what we see and observe and what actually occurs in these nuclear reactions. So in the past, we've had a look at unpacking electron volts, and we've said that the electron volt rescales our measurements of energy. When we're talking about energy at the atomic scale, measurements in joules are the best to use. This is because these measurements require us to use scientific notation for extremely small numbers, making it very difficult for us to conceptualize these numbers as well as the relative differences between the numbers. As such, measurements in electron volts make these measurements significantly more comparable. I'll demonstrate a conversion in the moment, but this conversion is quite simple because there is a simple ratio between units in electron volts and joules. Just like energy, measurements at the atomic scale in kilos have the same kind of inefficiencies or disadvantages. As such, we can scale this value in kilos to a single atomic mass unit. Both of these conversions are in your data sheet, and you'll also notice that for the atomic mass unit, there is another set of units that's measured in mega electron volts per c square. I'll get to this towards the end of this slide. So just to show you how these conversions work and how to express the mass of something at the atomic scale using atomic mass units, joules, electron volts, mega electron volts, and mega electron volts per c square, I'm going to go through an example where we do these conversions for the mass of a single neutron. The first thing that I want to do is convert our mass of a neutron from kilograms to atomic mass units. The way that this is achieved is by taking the mass in kilograms and dividing by the value in kilograms equivalent to one atomic mass unit. As the mass of the neutron is slightly higher than the mass of one atomic mass unit, we get a value which is just above 1 U. An easy check that you can do to make sure that you've done the conversion correctly is to have a look at the two values. The value in kilos for the atomic mass unit and the value in kilos for the mass of your particle. In this case, we have a value which is larger than the standard atomic mass unit, meaning that we should yield a number greater than 1. If we were to have flipped our numerator and denominator, we would have yielded a value that was less than 1, suggesting that the mass of the neutron is less than the mass of one atomic mass unit, which wouldn't make sense. If you do get a scenario like that, the easy solution will probably just be to flip your numerator and denominator, which is a fairly common process when we are doing unit conversions. This kind of check will work quite similarly for the rest of the conversions that we're doing in this slide as well. Next, I want to demonstrate how we can convert a measurement in kilos to a measurement in joules. To convert from a mass to an energy, we need to rely on Einstein's mass energy equivalence. By substituting into his famous formula E equals mc squared, we're able to yield a value that reflects the amount of energy that could be produced if all of the mass inside the neutron was converted into energy, and that's equal to 1.505 times 10 to the negative 10 joules. However, as noted before, this measurement in joules is not the easiest to work with. Therefore, we can convert to the electron volt or the mega electron volt. In this scenario, we take our energy in joules and divide by the conversion factor for an electron volt, and that gives us 9.395 times 10 to the 8 electron volts. We can also express this in mega electron volts by dividing by 10 to the 6, giving us 939.5 mega electron volts. You'll also notice in your data sheet that an atomic mass unit, which is a mass, can also be expressed in mega electron volts per c square. I'd like to take the time now just to quickly explain how and why that's actually achievable and why that can be quite useful. So if we were to rearrange Einstein's mass to energy equivalent for m, we get the equation that m is equal to E on c squared, which means that if we have energy divided by a c squared, it yields us a mass. So in the case of the neutron, because of its mass, it can be converted into 939 mega electron volts of energy, and therefore its mass can be expressed as 939.5 mega electron volts per c squared. We can also yield this number by converting our original measurement of mass for the neutron in atomic mass units that we did at the beginning. By multiplying the number of atomic mass units that we have by the mass expressed in mega electron volts per c squared for one single atomic mass unit, we yield exactly the same value. At the end of Module 7, when we started to unpack Einstein's mass-energy equivalence, we touched on the concept of mass defect, and we'll be touching on it again today as it plays a very large role in explaining the properties and behavior of nucleons as well as the nuclei of atoms and their interaction through nuclear processes. We unpack the idea that generally in nuclear processes, mass is not being conserved. That if you were to really accurately measure all of the matter at the beginning of the process and the mass of the matter at the end of the process, we'd find that there was more at the beginning and less at the end. Thus, there is a defect. There is a reduction in mass. And Einstein's mass to energy equivalent accounts for this mass loss. Essentially, the mass is being converted into energy. That transformation is leading to the release of energy in many different forms, which is observable in nuclear processes. And so what this means is there is a combining of the law of conservation of mass as well as the law of conservation of energy. We've previously thought about them as two separate concepts, but as we start to enter into the world of nuclear and quantum physics, and with an appreciation of Einstein's mass to energy equivalence, separating these two concepts becomes a lot less relevant. And that is because, as we've talked about before, there is this interchangeability between mass and energy, which in the everyday we consider to be quite separate from each other. As such, in these scenarios, if we find that mass has not been conserved and there is indeed a mass defect, it can lead us to the conclusion that the mass must have transformed into some form of energy. This mass defect is observable when forming a nucleus from individual nucleons. I'm going to do a little bit of math to demonstrate what I mean. Here, we're going to build a helium-4 nucleus from 2 protons and 2 neutrons. Based on the data in the table, I'm going to add up the mass of all reactant particles as well as the mass of all product particles to demonstrate that there is a mass defect when forming the helium-4 nucleus. According to our data, the helium nucleus loses 0.029729 atomic mass units worth of mass just by combining free protons and neutrons to form the nucleus. As talked about earlier, we can assume that this lost mass is being converted into energy. And so by converting between a mass and an energy value, we find that the energy that's being released is 27.3 mega electron volts. Where I want to go from here is starting to unpack why this energy is released in the first place, as this is a concept that we are yet to discuss. This loss of mass and release of energy can be explained when unpacking the concept known as binding energy. Now, based on the name of this energy, it's really easy to assume that this is an energy that the nucleus itself has. And it is this energy which holds all of the particles in the nucleus together. It's a fair inference to make, but it's actually kind of the opposite. Instead, binding energy is the total energy required to completely disassemble the nucleons inside the nucleus of the atom. Another way of articulating this concept is that it's the energy required to overcome the strong nuclear force inside the nucleus of the atom. It's kind of like talking about the energy required to boil water. It's not energy that the water itself has yet, but if it was to receive all of that energy, it would raise the temperature of the water from, say, its room temperature to boiling 100 degrees. Now, generally speaking, the higher the mass number and atomic number of a nucleus, the more binding energy it has, the more energy required to break apart all of those particles. However, just because an atom has a lot of binding energy does not necessarily mean that the particle is stable. This is because the particle is always experiencing destabilizing forces as well, the primary one being Coulomb repulsion between the protons. As such, if we want to understand and compare the stability of individual nuclei, we have to compare through looking at the binding energy per nucleon. In other words, how much mega electron volts of energy is required to separate one of the nucleons from all of the others. The most stable nucleon will have, of course, the highest binding energy per nucleon as a result. And when we do that, we yield a graph that looks like this, and this is quite a common and famous graph to look at and analyze. And what we see is that as we get in our early elements, heavier and heavier ones, the amount of binding energy per nucleon spikes up quite quickly. And it actually peaks at our iron 56 nuclei up the top over here. Iron 56 is the most stable nucleus in existence because its average binding energy per nucleon is the highest. After iron, you'll notice that these nuclei start to get progressively more unstable until we get to some heavy elements down the end over here, which are so unstable that there is no stable nuclei for any of these elements. They are always radioactive. So what makes these nuclei stable? The short explanation is that the nuclei with high binding energy per nucleon, the ones that are the most stable, are existing in low energy states. When the nucleons are in these low energy states, we maximize the magnitude of the strong nuclear force that they're experiencing. However, for a nucleus to stabilize in the first place, the particles need to lose energy to get into that low energy state. And as such, to achieve that, they remove energy essentially by dumping mass and releasing mass in the form of energy away from the nucleus itself. This is where our mass defect and energy release comes into account and where we see and observe it in a variety of nuclear processes. In our example in the previous slide, we were taking protons and neutrons and forming a helium nucleus. As the protons and neutrons start to form a nucleus, they lose energy as they enter a lower energy state compared to being a free proton or neutron. And this loss of energy, again, is accounted for by the loss of mass due to the mass defect. In this scenario, the binding energy for the helium nucleus is 27.3 mega electron volts. We can also express this as a value of binding energy per nucleon by dividing by the number of nucleons. And this is approximately 6.8 mega electron volts per nucleon, which matches up approximately with the average binding energy per nucleon as plotted here in our graph. These concepts of mass loss, mass defect, the release of energy, and nucleon stability are all connected to a variety of different nuclear processes. We call these nuclear transmutations. Essentially, they're a process where the nucleus of an atom is altered in some way, shape, or form, leading to the creation of a new element or elements or isotopes. In essence, each of these transmutations are some sort of process which leads to increased stability in the daughter nuclei, the ones that are being produced. Some of these we've already started to unpack before. We've looked at the idea of nuclear decay, things like alpha and beta decay, as well as particle bombardment. However, there's some other processes that we're going to be looking at today, like nuclear fission, which I did introduce in our Einstein's equal MC squared video at the end of Module 7. We'll also be unpacking the process of nuclear fission today. Let's start with fission first. Fission can, in the most simplest terms, be defined as the splitting of a nuclei into two or more smaller nuclei. Generally, a nucleus is going to undergo fission because it is highly unstable and is a heavy nucleus in the first place. There are a lot of scenarios where fission will occur, but first needs to be spurred on by some form of particle bombardment, which leads to a, relatively speaking, stable heavy nuclei taking on an extra particle and increasing the mass inside the nucleus, making an isotope or a new element which is exceptionally more unstable than the original particle. And this is what encourages the fission process itself. When we get this splitting happening, we form smaller nuclei. We also release some free neutrons, which is just the leftover additional mass. And we'll probably also get some gamma radiation and definitely some release of energy, which is going to be imparted into the nuclei and free neutrons. We actually already unpacked one of these processes in Module 7. For the nuclear fission of uranium, what we found was that particle bombardment was required to increase the mass of the uranium to begin with. Uranium-236 is significantly less stable than uranium-235 and undergoes fission to reach better stability. When we unpacked these slides in the previous module, we started to look at this concept of mass defect. And if we go through and apply the mass for all of the reactant mass versus the product mass at the end, we do find that, again, there is a mass defect, meaning that there is a release of energy. During this time, we also touched on the idea that the release of more neutrons could also lead to the attachment to another uranium-235 nucleus and continue the process on and on again, essentially leading to a chain reaction. We will unpack this concept a little bit further later on in this video. Before that, I also want to touch on the concept of fusion, because this is not something that we have really covered yet in this physics course. Fusion, in a lot of ways, is the opposite to fission. Instead of splitting an nuclei into smaller parts, we're instead combining two smaller nuclei to form a heavier one. This process, however, requires quite a lot of energy, and this is because we are bringing together two positively charged nuclei, meaning that they need to overcome Coulomb attraction before we can actually push them close enough so that the strong nuclear force can come into play and hold them together. However, what we will see is in this process as well, even though there's a lot of input energy required, at the end of the process, there will also be quite a large release of energy. That is because the heavier product is more stable of a nuclei and has more binding energy than the nuclei before it that were used to form the new product. So let's have a go at demonstrating the concept that nuclear fusion will release energy due to a mass defect. In this example, we are going to look at the combination of a deuterium and tritium atom, both hydrogen atoms, but carry one extra neutron and two extra neutrons respectively, compared to the more common hydrogen with just a proton in it. So these are combining and they are forming a helium-4 nucleus as well, like we did in one of the previous examples. However, there is an extra subatomic particle here, an extra neutron, and that doesn't actually form as a part of the final helium nucleus. Just like in the previous examples, we're going to have to account for the reactant mass, product mass, subtract that reactant mass from the product mass to determine the mass defect, and then convert to an energy using our E equals mc squared concepts. What we find is that in this scenario, the mass defect is equal to 0.0187 atomic mass units. And when we convert that to an energy value, there is 17.4 mega electron volts of energy, which will be released in this process. So we saw for both fission and fusion examples that energy was released in both processes. Let's go back to our binding energy concepts to try and explain how and why this happens. We already know that if we're going to break apart our nucleus, we must apply energy, and this is known as the binding energy. Essentially, if you add energy to the nucleus, it's going to put the nucleons in a higher energy state, getting them to a point where they're able to separate from each other and overcome the strong nuclear force. For nuclei which are naturally stable, they have a high binding energy per nucleon, meaning that lots of energy needs to be input to separate them. And this is because they already exist in a low energy configuration. What that means is more energy needs to be input again to overcome those strong nuclear forces which are holding them together. And in both processes of fusion and fission, these processes are making the nucleons that exist at the beginning transition to a more stable and lower energy state. As a general rule of thumb, fission occurs in light elements all the way up to iron, and fission can occur in elements as we progress from heavier elements backwards to iron. In both instances, what we're seeing is binding energy increase. In both instances, whether we're talking about fusion or fission, nucleons are forming new nuclei which have higher binding energy per nucleon. As such, they are entering more low energy stable states and thus have to release energy in the process to achieve this. Thus the mass defect, thus the big release of energy. The last concept that I want to cover, which touches on a dot point which also exists in your syllabus, is the idea that we can have controlled and uncontrolled nuclear fission. In our uranium example, our unstable uranium-236 forms two daughter nuclei. While we looked at the formation of barium and krypton, there are also other combinations of nuclei which can be formed, and we can see that in the other parts of the diagram. But in each instance, there is a release of multiple neutrons, sometimes 3, sometimes 2. If these neutrons are able to interact with another uranium nucleus, forming another uranium-236, then it will continue to perpetuate this fission process. In this scenario, we have what we call a chain reaction. One fission reaction leads to more fission reactions. However, in this uncontrolled chain reaction, if we have multiple neutrons that are being formed, causing more reactions, then the volume of reactions that are being completed are going to increase quite quickly. Instead of one reaction, the next time we're going to have two, and in the next generation, we're going to have four, or a potentially even more extreme scenario. It's these kind of uncontrolled fission reactions which led to the development of nuclear weapons. And essentially, these nuclear weapons take advantage of the idea that multiple nuclear processes can be happening all at once in a very short amount of time, and a small trigger leads to quite a large number of reactions and a significantly large release in energy. In a nuclear reactor, say, which is being used to power electrical grids, we don't want something like this happening. We don't want our infrastructure just blowing up randomly, right? So what we need to do is control the fission process. And there are lots of different ways in which this happens. And we'll investigate this a little bit further in class. Essentially, what needs to be included is something called a moderator. And this moderator is some sort of matter that the neutrons must pass through. Some of them will be able to pass through. And this is necessary for the reaction to continue after one simple trigger. However, what the moderator is very good at doing is blocking a lot of the neutrons which are forming. And essentially, this moderating material, also possibly referred to as a control rod, needs to be calibrated in a way where enough neutrons are allowed to pass and hit more material, causing more reactions, but also block enough of the materials so that the fission process can be controlled and maintained without a complete nuclear meltdown. Something else to note is these moderating materials also have a role in slowing down the neutrons themselves. The neutron doesn't have to come flying into the next nucleus in order for it to be picked up. In fact, it can be ideal for the neutron to be coming at slower speeds when compared to the speed that they were originally ejected from. As mentioned earlier, it's these concepts which we will unpack in further detail in class. Thank you very much, everyone. In the next video, we're going to build on our understanding of nuclear reactions and apply these concepts to what actually happens in stars and how that leads to its characteristics and properties. But until then, have a good one.